And we should be having a recording. Okay, good. Good. All right. Well, I need to get another device with me in case somebody puts something in the chat which I cannot notice. Okay. All right. Okay. So let's talk about what's with that title, right? So that's the question. So the idea here is that what we are trying to discuss is like what is the difference between a comparison and non-comparison sorting algorithms? Because if you have noticed so far, what we usually do was in selection sort or insertion sort or even quick sort, all these kinds of sorts, sorting algorithms rather. If you have looked carefully, you would see that we are mostly saying, okay, are you less than or larger than? And then based on that, you branch, like you go left or right, you swap an element or you don't swap an element. How many swaps do you need to do? And so on and so forth, right? And this is why, like, this is one of the major reasons why comparison algorithms are actually never be able to break the log n barrier. So let's actually talk about that. So if I, for example, give you something like 2, 1, and 3, okay? And I ask you to sort these numbers. So if I tell you just sort them, sort the numbers. What you're gonna do is say, okay, how you would like to sort them from the smallest to the largest? Fine, I'm just gonna write in 1, 2, and 3, right? Now, there is also a valid solution for the sorting. If I ask you to sort it the opposite side, it's gonna be 3, 2, and 1, right? Now, the interesting part here is that when you are trying to sort a list of numbers, what you are in fact trying to find is a correct permutation of these numbers. So what is a permutation of numbers in general? If you would like to find a permutation of a number, you should actually take the number of elements, and then you just simply say it's a factorial. Okay, so n factorial is in fact your permutations, or the formula for calculating permutations of numbers. So we have here 3 numbers. That means it's actually 3 factorial, which actually means that's going to be 3 times 2 times 1, which is going to be 6. So there are 6 possible combinations of these numbers appearing. So you're going to have so we have right now 3, for example. You could have 3, 1, and 2, for instance. You could have 2, 1, actually 2, 1, 3 is already there. So 3, 1, 2, 1, 1, 2, 3, 4. I need 2 more. Which is going to be, so 1 here, 1 here, 1 in the beginning, 1 in the middle, 2 in the beginning, 2 in the middle, 3 in the beginning, 3 in the middle. We need 1s in the ends as well. So it's going to be probably 2, maybe 1 has to be at the end, and 3. So 3 never appeared in the middle, right? So 1, 2, 3, 4, 5. And there is a sixth one right now. I will not, I mean, I need to figure out how to find it. But in any case, just to prove a point here. 1 appeared twice, 3 appeared only once. That means you need to have a 3 in the middle, 1 and 2. Oh, there you go. Actually, we found all the 6 permutations. So what you are actually trying to do is, hopefully none of them has repeated so far. Nope, nothing has repeated. So you have 6 unique permutations of such a list. And what you are trying to do is to find the right, you are actually searching through a space of possibilities of what are the available permutations for a certain list of numbers. And of course, the bigger the list is, the more possibilities there are, right? The more comparisons you need to make. right? And the interesting part here is that the moment you start actually cracking down on one permutation, let's say, you start actually like minimizing your problem space. So you are always subdividing, you are always dividing your problem space like almost by two, by half, by half, by half. I'm gonna actually show a quick example, like a very simple example, just to drive the point across. But if you have, for example, let's say a 4 factorial, like a four number digit, you will end up with, I don't know, like what, 4 times 2, times 3 times 2 times 1, right? So 4 times 3 is 12, times 2 is going to be 24. So you're going to have like about what, 24 different combinations, right? So this is only just for sorting 4 numbers. And again, you are trying just again to go through all the possible combinations, trying to find the right combination. And because you are dividing your problem by half or by whatever number every iteration, you actually get a logarithmic growth. And this is why comparison algorithms are always going to be a little bit slower than their counterparts, which non-comparison algorithms, which we're going to discuss in a minute here. So let me give you an example what I mean by eliminating your problem space, right? So your searching space is going to be a little bit different. So I'm going to actually grab a different pen color here. I'm going to have, for example, a number, let's say 883, and another color, which is going to be, let's say, blue here, which is going to be 371. Is 371 visible for you? And 5.
It's visible.
Okay, perfect. 596. Okay, so let's say you have something like this, and I ask you actually to sort these numbers. Okay, when you're gonna sort these numbers, what's gonna happen is you're gonna actually say, aha, okay, if like as you see here, when I was trying to pull this off here, if you say, okay, if my numbers, I'm gonna sort them, for example, from the smallest to the highest. So for example, this is my smallest, right? So let's say I'm going to sort it from smallest to the highest. That means that the numbers, when the list starts with this number, there are only 2 possibilities are going to come afterwards, after this number, right? So the first possibility is going to be either you're going to get 883, or you're going to get 556. These are the only 2 possibilities that could happen. And if you pick one of those 2 roads, the only number which is left is the last one, which is, for example, 883. So from the smallest to the largest, this seems to be like the correct combination, actually, right? So this is what you are searching for. But let's carry on with this one. And if you actually like choose the other way around, the non-correct combination, or the stuff which you don't want, is going to be 556 here. Okay, so what about if my number started again? So let me put 556 a little bit farther here. What happens if this was actually the beginning? So you have 2 choices. The first choice is 883. The second choice would be 371. And then if you choose afterwards whatever one you would like, it's going to be yeah, so in case you choose 371, what is the only option is left is going to be 883, and the rest is going to be here, so 371. Okay, so if you choose this number first, you can either choose this or that, and once you choose one, there is only one left, right? So this is how it would function. Let's see with this one. So this one is, you're going to end up with either 556, or you will end up with 371. And then you would like to actually choose later which one comes after. So if you choose this one, it's going to be 556 is left, and right here is going to be 371. So if you look carefully, your problem can be actually described. Right now I choose something which is what we call, like, I would like to call it like a Blackboard friendly example that doesn't require a huge space to write and too much numbers in there. But if you look carefully, the problem is almost represented like a tree. If I had 4 numbers, you would have ended up with something like this. And then you have something like this, because you have so many possibilities of numbers coming afterwards. So let's say something like this. So the first number comes in, and then you choose one of those two. And then if you choose one, there's a next one. I can even add one here. And then if you choose one, you end up with the last number. So let me add actually more here, more nodes here too. Okay, so number 1, number 2, number 3, number 4, right? So you have 4 numbers to choose from. Okay, and with that many possibilities, 1, 2, 3, 4, 5, 6, 7, 8. So sorry. Okay, so we have 8 numbers to sort, and you are actually like trying to, or sorry, actually it should be 4 numbers to sort, but you have like more possibilities in the bottom, like what's gonna be coming afterwards. Right now I choose 3 numbers, so 1, 2, 3, 4, 5, 6. And in order for me to choose what is going to be the best one to do, is that I have to traverse this kind of binary, quote unquote, similar binary space, or a tree kind of structure, to find the correct permutation, right? And this is what all comparison algorithms do. They try just to do that. And for example, in our case, your correct permutation, for example, if you would like to do descending, which is mean from the largest to the smallest, you're going to get this guy. Sorry, let me, apparently I didn't click hello. How beautiful. Did it glitch? Oh, come on, for real? Okay, this is sad. I'll try to figure that out in a second here. And then the next one is going to be this guy. Okay, so you have these two possible combinations, from the smallest to the largest and from the largest to the smallest. And you're always, and if you are working with binary trees or anything that relates to binary trees, you're always cannot break the n log n or log n complexities. It's just simply, and it's inherent in the problem. You cannot break it there. So how can we break that barrier? How can we go even faster, right? This is the good question. So we're gonna actually discuss some of the interesting non-comparison sorts, but I need first to fix my pen, because writing with blue is fascinating, actually. And let's see, if I try to close this guy and launch OneNote again, will it actually work? Restarting always the best. There you go. So enter counting sort. So the first sorting algorithm that is actually very intuitive and very easy, and you will see how cool it is and super fast, is maybe counting sort. And it is the simplest. So I can say that the counting sort, the simplest, and you can see it's also the most inefficient simplest and most, the simplest algorithm that breaks the n log n barrier. Okay, so this is one of the interesting part about this. So let's assume for a second that you have an array. I'm giving you an array of numbers which has the following numbers: 5, 8, 4, 3, 2, 1, 1, 3, 5, 4, 6, 0. So let's say I'm giving you these numbers to sort. What you're going to do is your algorithm will allocate a new array, an empty array, okay? And the empty array will have a size of the largest element in the array. So the largest element in the array, so you're going to scan your array, you're going to find the largest element, and then you say, okay, I'm going to create another array, which is going to be having the largest element. So in our case, it's going to be 8, the size of it. So I'm going to create an array of size 8. So it's going to be, I'm going to write in indices right now. It's going to be 0 base. So 0, 1, 2, 3, 4, 5, 6, 7, and 8. So these are my indices to the array. Okay, and this is like, I'm gonna just just draw a line here. So here's your, like, this is the input. And this is what we call this array, which is going to be filled in a minute, is called the counting array. Okay, now you're going to scan the array. So you're going to say, okay, how many times do I see 5? So I see 5 once and twice, right? So I come here in the index 5 and I just write n2, right? So you can actually count it like this. 8, I'm going to increment it to 1. 4, I see it once. 3, I see it once. 2, I see it once. 1, I saw it once. Another one, increment that guy to 2. So I'm using these numbers as an index into the counting array, okay? 3, I saw it another time, increment. This is going to be 2. 5, we already have resolved it. 4, it's going to be actually incremented one more, right? 6, saw it once. 7 is nothing, so basically it's actually 0. So practically speaking, whoever you usually initialize your counting arrays to zeros, basically speaking, I just left them empty. And then the only thing which you need to do is write whatever you saw in the count back again into the input array. You usually like just override the input array. So I will not actually override it here. I'm going to write in the solution right away in the bottom. So this is your result. So 0 have been seen 0. So 0, actually 0 is here. So 0 has been seen once. Sorry about that. I forgot. So let me put this 1 because it's here, right? You guys write anything in the chat to warn me about crazy stuff that I might miss? Let's see. Nobody writes anything. Yo, people, please be awake. Now, let's see. So at index 0, so 0 has appeared only once. So I write 0 once. Let me write this in yellow. So so 1 has appeared twice. So I'm just going to write in 1 and then 1. 2 has appeared once. I'm going to write 2. 3 has appeared twice. It's going to be 3, 3. 4 has appeared twice. It's going to be 4, 4. 5 has appeared twice. It's going to be 5, 5. 6 has appeared once. 7, nothing. You don't write it. 8 appeared once. You are done. Sorted. This is how counting sort works. Now the question comes here is, do you know where's the problem with this method?
Is it because it creates space for a number that isn't there? For example, in this, it's 7, so it creates a memory for 7, but there's no 7.
Okay, so this is you are actually, yeah. So this is you are actually close. You are actually close, but but basically speaking, if I give you to sort, but you are, I mean, you are really close to the answer. If I give you to sort something like 1, 2, and 10,000, right? And I tell you sort this array, the counting sort relying on the idea that you're gonna find the largest number, and then you allocate an array with the size of the largest number. The problem with that is if I'm actually having 3-element array and I have a 10,000 right there, I'm gonna allocate a 10,000 array element, like an array with a 10,000 element size, just to sort 3 numbers, and it's going to be 1, 2, and a bunch of zeros until 10,000 at the end, right?
Yeah.
So practically speaking, this is your issue. So it actually, counting sort is super fast, but it's really, really memory hungry thing, right? So here's the interesting part. Cons, also pros, super fast, right? Practically speaking, how many numbers do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So practically speaking, you could have had, so you could have had like n factorial, log n factorial of comparisons, right? Because as we said, we are breaking down through a tree. So practically speaking, if n factorial of if we say n factorial is going to be like, this is 12 factorial, the numbers which you are trying to sort, you're going to end up with this number 4, 7. I actually written it down just for your amusement here. 1, 6, 0, 0. These are the amount of possible combinations these numbers can be rearranged, right? So if you actually take the log base 2 of 12 factorial of that number, you're going to end up with approximately 29, which is in fact like approximately 29 comparisons until you get to the right combinations. Here we didn't do any comparisons. We just simply like flew through. We just simply made the almost like it's an n. It's actually O of n. This whole thing was O of n, counting sort. And let me just put this thing right there, O of n. The fastest sorting algorithm, the comparison-based sorting algorithm we know of so far is quicksort. Maybe there are alternatives and other stuff, but they are usually they are always in that n log n space most of the time. So n log n is actually slower than n, just to be clear here. All right. So we don't do any of that stuff. We don't do any comparisons. What we do is we actually call the cons is so if you do like super fast has been so 29. Hang on, let me write this in a good sentence. Comparisons has been avoided. Cons requires a lot of memory. All right, so this is not nice. We need to make this a little bit better. So what we're gonna do, we're gonna look at another variation of this, which we're gonna be calling it, or it's actually called bucket sort. And a bucket sort, sometimes it's also called radix sorts with buckets, actually. Okay, so sometimes it's actually called that way too. So if you encounter somebody mentions it in that way, do not be scared or do not be like, weird and stuff. So assuming that, and I'm actually going to write in a little bit larger numbers because this is how it works, because you're going to see the benefits of it in a minute. So you're gonna have, let's say you're gonna have, if I give you the following numbers, so 461, 771, 683, 883, 034, 405, 895, 966. Okay. Now, similar to counting sort, similar to it. Bucket sort, what it actually asks you to do is you create something which is called buckets. And you can imagine them like literally like it's going to be you can think of it like stack or linked list or whatever. We're going to talk about this later, but generally speaking, you create a bucket. And how many buckets do I need? So you create buckets based on the number base you are working with. So we in math, or generally like the general purpose stuff which we are using base 10 here, right? So we are having numbers running from 0 to 9, and then the more numbers you add, you are always working with base 10, base technically speaking, right? So you can add hundreds and thousands and tens of thousands and millions and so on and so forth. So we're going to create buckets running from 0 to 9, just because we are working with base 10. So I'm going to have buckets like this. So I'm going to have the 0 bucket, the 1 bucket, 2, 3, 4, 5, 6, 7, 8, and 9. All right. So these are my buckets. And I measured them something like this, by the way. Okay. But I'm not gonna draw it here right now. I'm just gonna draw it after I'm done with stuff, so you can like see. I'm gonna try to make it this as Blackboard friendly as possible. And the first iteration will throw you off in a minute, and you will see in a minute why. But it's actually good that you can observe some interesting stuff. Now, once you create the buckets, so you got the input array, you created your buckets based on the base number which you are working with, which most, let's say, is going to be base 10 all the time. Then what you're going to do, you're going to look at the least significant digit. What does that mean? So if I actually grab a number like 461, so let me actually write this somewhere. Oh, hang on, sorry about that. 461. Yeah, why not? I'm just going to write it here. So 461. This is the least, hang on, least significant. My pen is glitching, sorry. Significant digit. This is the most significant digit in English, okay? Mathematically speaking. So if you would like to get that number, okay? Sorry about that. So if you would like to get, for example, let's say the number 6, for example, or let's say, okay, let's actually start from number 4. So let's say you would like to get the most one. You're going to say 461 divided, sorry, I said divided by 100 modulo 10. You're going to actually get the 4. If I give 461 divided by 10, modulo 10, you're going to get actually 6. And if I say 461 modulo 10 is going to give me 1. Okay? So this is how I can get each one of those guys using these formulas. Okay? So when I ask you to say, okay, when you are implementing bucket sort, I'll ask you to grab the one of these numbers, all what you need to do is run them through these formulas, and then you're going to get each one of these numbers in that way. All right?
Okay.
Okay. Now, so as I said, we look at the least significant digit, which is the 1 in this case, right? So I say, okay, let's scan the array. So 461, I'm looking at this. 1 goes to the ones bucket. So it's going to be here 461. Moving along, 771. This is 1. I go to the ones bucket. I'm just going to write in 771. 683. I'm looking at the 3. Goes to the 3 bucket. It's going to be 683. 883. I go to the 3 bucket because I'm looking at the 3 here. Go to the 3 bucket, 883. 034, I'm looking at the 4. 034, I go to the 4 bucket, right? 405, I look at the 5, look at the index 5, the bucket 5, right? And I'm just going to write in 405. 9895, looking at the 5, you go back to the index, and then you say 895. 966, so you look at the 6, you go to the bucket 6, and then you write in your number, right? So 966. The rest of the buckets are empty, which is fine. Okay. The next step is to take the numbers from your bucket and write them back into your input array. So I'm going to actually write them down in the bottom, all right? So I will not overwrite this. So I'm just going to just mark these guys like so, like so, like so, like so. So in case you are looking at this blackboard later on when you are studying, you have some reference. And let us actually write this down. So this is my input, right? And right here, I'm just going to draw a line. I'm just going to write this input. This is iteration number 1. Right now, we're going to look at iteration number 2 in a minute. So what you do is you loop over each one of those buckets and you take out the elements. So I'm just going to take that out from the bottom up like so. So here is going to be 4, 6, 1, because 0 has nothing here. Then we have 7, 7, 1. 2 doesn't have anything. 3 has 6, 8, 3. 8, 8, 3. Then 4, 0, 3, 4. Then 5 has 4, 0, 5. Then 8, 9, 5. Then 6 has 9, 6, 6. And you are done, right? Because there are no buckets in there. There's nothing in these buckets. Now, if you obviously look at this, you're going to tell me, Mohammed, I've just got the same array. And I tell you, you are right. And it has to be. Because if you look carefully, these numbers, these little guys here, these guys, are actually sorted already. Look at this, 1, 1, 3, 3, 4, 5, 5, 6. They're already sorted. So you can, if you are in the middle of the exam and you screw up a step, you can actually sanity check one of the middle steps. Let's say you make a mistake right when you are checking for this guy. If you copy the output or if you copy stuff from the buckets into the input array back again, and if you, while you are copying, these numbers are not sorted in terms, at least in the middle, then you are doing something wrong, right? And you will see in a minute how this will work again when we do the second iteration. So the second iteration comes in. Again, we're going to have the buckets. Of course, once you are done with the copying, you empty your buckets, right? So 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Sorry. And right now you're going to actually look at the second digit, right? So we looked at the least significant one. We're going to look at the middle one right now, which is using this formula, right? So right now you're going to look at, we're going to look at these numbers. Let me just highlight them for you. There we go. And now let's scan the array. So 4, 6, 1. So we go to the 6 column or the 6 bucket, and then we write in 4, 6, 1. 7, 7, 1. We look at the 7th bucket. We're going to write in 7, 7, 1 because we're looking again at this guy. 6, 8, 3. We go to the 8th bucket. It's going to be 6, 8, 3. 8, 8, 3, which is going to be 8, 8, 3. 0, 3, 4, we look at the 3, go to the 3 buckets, and then we're going to say 3, 0, 3, 4. 405, which is going to be 405 because we need the 0, right? 8, 9, 5, so the 9th bucket is going to be 8, 9, 5. And then 9, 6, 6, which is going to be here. So because we'll look at the 6, so 9, 6, 6. Okay? And right now we do the second iteration, right? Right now we fill in our buckets. Sorry, we empty our buckets. So I'm just gonna draw a line here again. I'm gonna write in the input because it's gonna be an input again, right? And let me draw a little bit of an arrow here because you are transferring whatever in the bucket into the input, right? So this is whatever in the bucket, we transfer it into the input. And right now we scan the array. So 405 comes first. So 405. If I know how to write today. Oh, come on. 405. Then the ones bucket doesn't have anything. The twos bucket doesn't have anything. The three bucket, however, has 3, 0, 0, 3, and 4. 4 bucket doesn't have. 5 doesn't have. 6 has something, so it's going to be 4, 6, 1, 9, 6, 6, 7, 7, 1, 6, 8, 3, 8, 8, 3, 8, 9, 5. Okay. Now here's the interesting part. If you look at this array, it is not sorted, obviously. However, if you would like to sanity check, if you would like to make sure that you are not making any mistakes, look at these numbers because you were sorting by them, right? All of them are actually sorted, right? So look at this. You have 0, you have 3, you have 6, 6, 7, 8, 8, 9. So there are no mistakes in there. They are actually sorted, but they are sorted by these middle guys, right? So I just wanted to show you that you can keep track of if you are making a mistake, if you are doing this by hand, or if you are programming this by hand. And right now we're going to do the third and the last iteration. So this is actually iteration 2. This was, sorry, iteration 2. And right now we say iteration 3. Again, we're going to make our buckets. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And right now you look at the most significant digit, right? Right now we're going to actually look at this number, right? So let's see. 4 is going to be actually 405. So we're going to write it here, 405. 0, 3, 4. So it's going to be 0, 3, 4. Again, we are looking at this now. Let me just highlight them for you. Right there. Okay. So 0, 3, 4, 4, 6, 1. 4, 6, 1 is going to be right here. 966, so 966, 771, which is going to be 771 here, 683, which is going to be here, 883, and 895. And then right now we copy whatever we have in our buckets into the input array, which is going to be our sorry, final output. So I'm going to just write it here. So final output. You're actually copying that stuff into here. So at the 0th element, you're going to have only one in the bucket, which is going to be 0, 3, 4. This is the only guy in there. 1s and 2s and 3s are empty, or happens to be so. And 4th index is going to be having, so that the fourth bucket, we have 405, 461. The fifth bucket doesn't have anything. The 683 you have, so 683. Then 7th bucket we have 771. Then the 8th bucket we have 883 and 895. Then we have 966, right? And this is it. You got actually your array sorted. So 0, 3, 4, 405, 461, 683, 771. Yep, that's it. So as you can see here, we have actually managed to sort the array like in 3 cycles based on the number of digits you have in a number, right? So the complexity of this guy is actually O of n plus b, where b is the number of digits. So b equals to number of digits within a number. Okay, so if you have 4 numbers, then you're going to have 4 iterations. You can have 5 numbers, you're going to have 5 iterations, and so on and so forth. Okay. Now, the problem with this is the problem with bucket sorts in general. Computers do not have buckets, actually. There's no such a thing as buckets, right? When you think about this. And then the issue will arise and you will say, okay, how are we going to implement this thing? And then you can talk about stacks or queues or linked lists and stuff like that. Probably linked list would be the only viable solution, so you don't have to allocate and unallocate automatically expanding arrays and stuff like that, because automatically expanding arrays meaning that let's say if you're using, for example, like you could tell me, Mohammed, I'm going to use the list of T in C# to implement this thing. However, the problem is list of T will allocate, for example, let's say 10 elements, and then once you grow out of this, it will destroy this guy. Actually, it will. Before it destroys it, it will recreate for you 20 element array, copy the stuff, destroy this, and so on and so forth. So imagine that while you are building your buckets, you are actually like automatically expanding and shrinking stuff and deleting memory, and it's going to be actually quite a memory hog. It's actually quite it's actually like too much of too much memory transactions are happening in there. So linked list would be a little bit better in this case, but still keeping track of these stuff and eliminating these linked lists or removing them from memory is still, this memory management bit is a little bit interesting to handle. So there has to be even a better way of doing this. So a better way of doing this is what we know radix sort, which again can be called sometimes radix sort with counting sort. Okay, and this is going to be like I'm actually like running with you without a break here because this is going to be the final bit. So let's actually get this done. All right. So enter radix sort. AKA, also known as radix sort with counting. Okay. Now, how this thing work? So we have, assuming that we have the following. So I'm going to actually use the same numbers here, and we're going to end up with somewhat similar outputs, but let's see. So we assume that you have 4, 6, 1, 7, 7, 1, 6, 8, 3, 8, 8, 3, 0, 3, 4, 4, 5, 8, 9, 5, 9, 6, 6. Okay, assuming that I'm giving you an array like this as an input, your algorithm will allocate two arrays. One is the output array, and the second one is going to be your count array. Okay, so I'm going to create, so this is your input. I'm going to have an output array. Which is going to be the same size as the input array. And I'm going to have here something which is called the count array. And the count array has the maximum number of digits based on the base you are working with. So we are working with base 10. So our count array is going to run from 0 to 9. Again, we are doing it like with counting sort. So, so you're going to have here 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Sorry. And then we're going to scan the array and we're going to count. We're going to actually look at, oh, excuse me, just give me a second here. Apologies, I need just a drink of water because apparently my voice is failing me for a reason. Okay. Now we're going to scan the least significant digit in the same way we did with bucket sort. All right. And let's scan for this. So you look at sorry. So 0, there are no numbers. Actually, well, there is 1. So oh, sorry, we said the least. So we have the 6. So we're gonna actually look at the first iteration. We're gonna look at the 6, 5, 5, 4, 3, 3, 1, and 1. This is what we are looking at. Okay. And now let's see. So we're gonna scan this. So 1, it has been seen once. Then it has been seen another time, which is gonna be 2. 3, 1, 2. 4 has been seen only once. 5, 1, 2. 6 has been seen once. So 2s, we don't see any 2s in the least significant bits, so it's also digits, so it's going to be 0. 0 doesn't have any, doesn't exist anywhere, right? When we are looking at this. And 7, 8, and 9, there are no numbers ending with 7, 8, or 9, which means this is going to be 0, 0, 0. Okay. Now, the next step, what we usually do, we do something which is called the prefix sum. Now, the prefix sum means that you take one element, sum it with the previous element, and override it. Again, so you take, for example, this 0, sum it with whatever was before it, and then put the result in here. Okay, so 0 will stay the same because there's nothing before 0. So 0 is still the same. 2 plus 0 equals to 2. You write 2 back. So 2 is still the same. Fine. 0 plus 2 is going to equal to 2, right? And then you write 2 here. So if I actually write here the prefix sum result is going to actually look like this. So if I have a 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, again, this is my count array. By the way, this should be replaced in the count array. I'm just writing this here again, just to give you like a reference of what's happened. So I can say prefix sum. So this is counting array after the prefix sum. Okay, so I'll just simply take out the result because there's no need for it. So counting array after the prefix sum is going to be this one. So 0 plus, so 0, it's still the same because there's nothing before it. Even if there's 10 here, there is nothing before it, so it stays the same. 2 plus 0, so 2 plus 0 is going to equal to 2. So we override it here. So our counting array will have something like this. So 2 plus 0 is going to equal to 2. And right now I would like to know what is this number. So 0 plus 2 is going to equal to 2. Then I would like to know what is this number. This number became 2 actually, right? So 2 plus, freaking hell, hang on. Yeah, because having this is going to be actually a little bit difficult to see. Yeah, I need to yeah, fine, doesn't matter. I need to keep track of this. So it's going to be actually, this should be actually 4 right now here, right? Because if this becomes 2, right? Because if I would like to figure this guy's out, so 0 plus 2 is going to be 2, so 2 is here. And if I would like to figure this guy out, it's going to be 2 plus 2 is going to be 4, right? So actually, I could have written this in a highlighter, but it doesn't matter. So this becomes 4, right? So this guy is right now 4. 1 plus 4 is going to equal to 5. So this is how your prefix array, I'm just replacing this. So this 1 will be replaced with 5. So if this is 5, I would like to figure out this number. 2 plus 5 is going to equal to 7. So 7. And this guy became 7. 1 plus 7 is going to be 8. Take this out. So this is the 8. 0 plus 8 is going to be 8. And this became 8, right? 0 plus 8 is going to be 8. And this became 8. And if I would like to figure this guy out, I'm just going to say 0 plus 8 is going to be 8. So if you do the prefix sum in place, because I actually had to offload it to another array just for you to see stuff, but you have to do it in place. And if you did it in place, you will get this. Okay? Does this make any sense? Guys? Did I confuse
Yes,
you?
it does.
Okay, do you want me to write this? Is it better to write it as a copy for you, or would you like me to replace the counting array?
Maybe as a copy for later when we look at the material. So we have.
Okay, okay. All right, fair enough. Now what we're gonna do in this case, we're gonna actually scan the elements from right to left. And I'm saying these elements. Okay? You're gonna scan them from right to left. And you're gonna put the stuff into the output array. Right now, this counting array, which you see, is right now this guy. Okay? Here, after the prefix sum. Okay? So this is my first iteration. Iteration. Oh, come on. So this is iteration 1. Okay? Here's what we're gonna do. You scan from the right. So 6. You go to the bucket. You go to the counting array 6. You see what is in here. These numbers right now, which we have calculated the prefix sum of, is in fact our indices into the output array. So the output array has 0, 1, 1, 2, 3, 4, 5. Let me write this a little bit farther. 5, 6, 7, 8, 9. I don't know if I added more than I should, but 0, 1, 2, 3, 4, 5, 6, 7. Actually, I put 2 more. 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, actually, I added 2. So I'm gonna actually go here. 6. So I actually looked at the I'm scanning from here. Okay. 996. Looking again at this guy. You go to here, to the index 6, in the prefix, in the counting array after the prefix sum. You look at this 8. You say, okay, minus 1. Minus 1 is going to be 7 because the prefix sum gives me an array of based 1, and we are working with a base 0 array, so we're going to subtract 1. So here's going to be minus 1 is going to be 7, so I'm going to write in 7. 7, that means that this guy will go here, 9, 6, 6. Okay? Then moving along, okay. 8, 9, 5, 5. We go here, the index 5, minus 1 of that 7. So that 7 minus 1 is going to be 6. 6. So this 8, 9, 5 is going to actually land right here. Then we go again. We get 5 again. So we go to 5 minus 1 to that number 6. So it's going to be right here 5. So it's going to be 405. Then we say 0, 3, 4. We go to the index 4. So this 4, go to the index 4, take that number, minus 1 is going to be 4. That 4 is going to be 0, 3, 4 right here. So 0, 3, 4. Okay? 3, you go to 3. To that number minus 1 is going to be 3. You take that, you put it here. So 8, 8, 3. You look at again the 3 here again, 6, 8, 3. You go to 3, the index, minus 1 is going to be 2. You take that number, you put it at index 2, so 6, 8, 3. Sorry, 7, 7, 1. So 1, you go to the index 1, minus 1 is going to be 1. So you put it here, 7, 7, 1. Here, 4, 6, 1. You go to 1, minus 1 is going to be 0. You go to index 0, is going to be 4, 6, 1. This is your output array. what you usually do, you swap the pointers if you want to, or you can just simply copy whatever the output into the input. It's up to you. And right now we go to the next iteration. When you go to the next iteration, you zero your count array and you do the iteration back again. So let me do iteration 2. I'm going to actually write in the input again. So here's your input array. You clear the output array, obviously. So you're going to have here 4, 6, 1, 7, 7, 1, 6, 8, 3, 8, 8, 3, 0, 3, 4, 4, 0, 5, 8, 9, 5, 9, 6, 6, and I hope I didn't forget anybody. You have your count array, which is zeroed out. It's all of them, everything is written 0 in there, so I'm not gonna write it there. I'm just gonna write in the indices. So we have like 0, 1, 2, 3. Hang on, sorry, I need the output as well. So let me write in output array. So it's gonna be like 0, come on, 0, 1, 2, 3, 4, 5, 6, 7. And then we have the count array. Count array from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are my indices. I'm just writing indices here. And right now we do the second iteration. We look at these numbers right now. Right? So we scan the array and we do the counting. So 6 has been seen. So this is my counting array. So 6 has been seen 1. So I'm going to write in 1, 7, 1, 8, 1, another 8, increment to 2, 3, put in 1, 0, put in 1, 9, put in 1, 6, put in 2. And now we do the prefix sum again. And obviously, this is 0, 0, 0, 0. So whoever doesn't have a count, it just simply defaulted to 0, right? So I'm going to have here a prefix sum count, or sorry, counting array, and this is going to be counting array after prefix sum. Okay, so let me write this again down. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Now let's see, because this is going to be the first element, 1 is going to be always 1 there because there's nothing before it, so it stays the same. The 0 is going to be saying what? So 0 plus 1 is going to equal to 1, so we write in 1. So this becomes 1. 0 plus 1 is going to be 1, so we write in 1, right? So this guy becomes 1. So 1 plus 1, it becomes 2, so we write 2. So this became 2. 0 plus 2, so it's this one also became 2, so that became 2. 0 plus 2 again, so this became 2, and this became 2. 2 plus 2 is going to equal to 4, so this became 4, right? 1 plus 4 is going to equal to 5, so this one became actually 5. 2 plus 5, this became 7, right? So this became 7 when we replace it. 7 plus 1 is going to be 8, and this became an actual 8, right? So I'm just simply highlighting it on the top so we can actually keep track of the stuff. So counting array after the prefix sum. Okay, good. Hopefully I didn't miss anything up. So let's see. I didn't hear, sorry.
Everything's good, everything's good.
Okay, okay. All right, so what we do, we actually right now scan the array from right to left, and we write in the stuff into the output array. So let me scroll this up a bit. All right, so let's see, from right to left, 6 we go here, -1, so this was actually 4. I don't know why my 4 was weird. What the hell? The pen, actually, somehow like the digitizer is glitching for some reason. So anyway, so this was 4. -1 is going to be 3. We look at 3 in here. This actually has been done. We don't look at this, by the way. So 3, you're going to actually put in 9, 6, 6. Let's see, 8, 9, 5. So 9, it's here. -1 is going to be 7. Is going to be 7. 7, I will write in 8, 9, 5. 405, so this is 0. 0 right here. -1 is going to be 0. So 405 goes right here. 3 goes here. -1, so it's going to be 1. So 0, 3, 4. 8, 8, 3, so 8. 8 is here. -1 is going to be 6. 6 and my output array is here. So 8, 8, 3. 6, 8, 3 is going to be again 8. -1 is going to be 5. 5, so it's going to be here. So 6, 8, 3. 7, 7, 1. So we go to 7. -1 is going to be 4. 7, 7, 1. 4, 6, 1. So 6 -1 is going to be 2. So we go to the index 2. 4, 6, 1. And for sanity check, so we can make sure that we are doing everything right, the middle numbers, they should be sorted. So 0, 3, 6, 6, 7, 8, 8, 9. So they are sorted. So we are actually still on the right path. So we didn't make a mistake in the middle, which is good. And now the final iteration. Actually, right now, it is the time for you to clear your counting array. So you clear this counting array or the prefix sum array. You swap the input and the output, and you clear the output array or whatever you would like to do with the operations. The main thing is that you need to start with a fresh output array or a clean output array, and the new input is going to be these elements and the 0 counted array. So let me write. Actually, let me see if I can. Can I actually copy this thing? And yeah, I can move it. Can I copy that thing? Yeah, fine, I will not waste time. Doesn't matter. Come on. Okay. Bro, I need to figure that out with a shortcut maybe. Let's see. So this was iteration 2, I think. It was iteration 2. And then we go to the final iteration where my input is going to be 405, 0, 3, 4, 4, 6, 1, 9, 6, 6, 7, 7, 1, 6, 8, 3, 8, 8, 3, 8, 9, 5. Okay, this is my input. Here's my output. And it's going to be 0, 1, 2, 3, 4. I swear it's glitching. But okay, 5, 6. What the heck? 5, 6, 7. And then we have our counting array. Which is going to run from 0 to 9. Okay, let's see. Now we scan for these guys, for these bad boys, right there. Okay, we put them in our counting array. So 4, seen once, 0, seen once, 4, increment, 9, seen once here, 7, seen once, 6, once, 8, once, another 8 is going to be 2, right? We do the prefix sum. So, of course, obviously, these are all zeros. 0, 0, that's it. So counting array after prefix sum. Okay, which I'm gonna write again 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let's hope that you guys it will be useful for you during studying these materials then. So 1 stays the same because there is nothing before it. Then this 0, so we say 0 plus 1 is going to be 1, so this is going to be 1. This became 1. 0 plus 1, this one became 1, so it's going to become 1. So 0 plus 1 will be 1, right? 1. And this became 1. 2 plus 1 is going to be equal to 3, so this became actually 3. 0 plus 3 is going to be 3, and this became 3. 1 plus 3 is going to equal to 4, so this became 4. 1 plus 4 is equal to 5, so this became 5. 2 plus 5 is becoming 7, so this became 7. 1 plus 7 is going to equal to 8, so this became 8, right? So right now, this is my, I'm just, again, I written it here for myself as a reference so I don't get lost. And right now, this is your counting array after the prefix sum. We look at only this guy for now, okay? So we look at this. And now we do the scanning. So we scan from right to left. 8. 8 is here. Minus 1 is going to be 6. So this is going to be 6. We insert that here. So 8, 9, 5. We look at here again. We see 8 minus 1 is going to be 5. So 5. So 5 is going to be, sorry. 895. And number 5, so we said 883 is going to be 883. I just didn't notice I written it in the wrong index. Let's see, so 8, 8, so 6 here, so 6 we go to here. 4 minus 1 is going to be 3. So 683 will go at index 3. 7, we go to the index 7, has 5 minus 1 is going to be 4. 771 goes to index 4. 966, so we go to index 9. 9 has 8 in here, minus 1, it's going to be 7, so we take 966. 461, 4, index 4 minus 1 is going to be here 2. So 3 minus 1 is going to equal to 2. 4, 6, 1 goes here. 0, 3, 4. You look at index 0, has 1 in it. Minus 1 is going to be 0. So 0, 3, 4. 405, 4. You go to index 4, it has number 2 in it. Minus 1 is going to be 1. It's going to be 405. And your array is sorted. So 0, 3, 4, 405, 461, 683, 773, 4771, 883. Okay, perfect. So this is actually sorted. So it took actually 3 iterations. So the complexity of this guy is O of n plus b, where b is the number of digits you are working with, the base, basically, the base number of digits you are working with. So if you are working with, sorry, the number of digits you are like having, so if it's, let's say, 4 numbers or 5 numbers digit, that means you have 5 iterations and so on and so forth. And it is still relatively fast. Now, this is radix sort. What I would like to mention here is, before I let you go, that there are a couple of facts you need to know. There are many variations of radix sorts, and there are many variations of quicksort. There are quicksorts, for example, with 2 pivots or 3 pivots. You have radix sort where we scan from the least significant bit to the most significant bit, and then you have, or the least significant digit to the most significant digit, and then you have radix from the most significant digit to the least significant bit digit. It's actually written like this. So you have radix least significant bit, and then you have radix most significant bit. You have these 2 variations. We are actually, so far, when we worked with this, we worked with the least because we always started from the right here. So we start from the least and we move forward. Statistically speaking, it has been proven statistically that the LSB version is faster. When people run the analysis and statistics on this, when they like put in random numbers and they tried it, somehow it just shown that statistically it's actually better. Radix sort is good if you are trying to sort an enormous amount of numbers. So for example, quicksort, it doesn't pay off to use radix sort, let's say, if you would like to sort 1,000 numbers, for example, right? But once you get into 100,000, a million, or something like that, when you would like to sort million numbers or more, right now you need to like consider something like radix sort because it will be way, way faster than quicksort. So quicksort is like having this, it can be easily like used in like relatively smaller ratios, tenth of thousands, 100,000 maybe. I mean, maybe, yeah, but basically speaking, radix sort, if you break that number, like you are trying to sort something that's huge, like huge list, radix sort will definitely actually like be helpful there. I think this is it when it comes to radix sort, and I will hang on, need to stop recording right here.